Well, good afternoon. This is David Sybeck in Maryland. Welcome to our seminar series. It's my distinct pleasure to introduce Professor Jim Drake from the University of Maryland today. Jim received his doctoral degree at UCLA and began teaching there, but he soon left for the University of Maryland as a postdoc, where he became a teaching faculty member in 1985. He's now a distinguished university professor and director of the Joint Space Science Institute, which is a collaboration between the University of Maryland and Goddard Space Flight Center. He's also the director of the NASA Drive Center on Solar Flare Energy Release, or SOLFR. He's a fellow of the APS and of the AGU, and he is the winner of the James Clerk Maxwell Prize in Plasma Physics. Today, he's going to be talking to us about magnetic reconnection and the structure of the magnetopause. I'd like to remind you to mute yourself during this presentation. Also, that this presentation is being recorded. If you have questions, please enter them into the chat box at the bottom of your screen, and we will be asking them at the end of this presentation. And now I'd like to pass the presentation over to Professor Drake.
So thank you, all the organizers of this, and then thanks to all the attendees. So in preparing this talk, I'm going to try to introduce the concept of reconnection by pretty much going back to the basics. And so hopefully, even if you don't have a lot of history in this field, you'll be able to get an understanding of what's going on. And then, of course, as we progress through, I'll approach the more recent issues that have come up in light of both simulations and observations. So it'll be pretty much state of the art by the end of the talk. But at the beginning, I'm gonna start with some pretty basic stuff. So let's see if I can get this thing to switch. I assume everybody can see my cursor. So I'm going to use that. I think that will help. So here's a general slide talking about magnetic reconnection and the dynamics of the magnetosphere. So magnetic reconnection between the solar wind and the Earth's magnetic field is a fundamental driver of the dynamics of the magnetosphere. There was a Sentinel paper in 1961 by Jim Dungy in which he proposed that the solar wind magnetic field, shown with the southward component here, would reconnect with the Earth's magnetic field with its northward component. But of course, many people didn't believe in reconnection at the time, and so there was a lot of skepticism by some people. However, in the end, it turns out he was right. And reconnection on the front side here leads to magnetic flux being transferred into the magnetotail and producing an extended magnetotail as drawn in this picture. This was, by the way, Margaret Kivelson's picture. And of course, the reconnection then that goes on in the tail produces a lot of energetic particles there and injects flux as well as energized plasma into the inner magnetosphere, where it plays a major role in the generation of the radiation belts. And then this flux wraps around the sides of the Earth and then comes back up to the front side, and that sort of completes the circulation of flux that makes up the dynamics of the magnetosphere. Okay, so that's just sort of a basic introduction of the important role that reconnection plays in magnetosphere dynamics. Okay, so here's an outline of my talk. At the beginning, I'm going to really go over the fundamentals of reconnection, some of the fundamentals, and I will show you some data. And most of this discussion is going to be sort of pre-MMS physics. And then we will go on to what's going on in the so-called MMS era. And in particular, I'll talk about reconnection at the magnetopause and some important things that have been discovered with the MMS observations, as well as simulations that have been in support of those observations. Now, when I was originally planning this, I also had planned on talking about turbulent transport at the magnetopause, and in particular, the implication of the observations that electrons remain largely frozen in the turbulence that they do measure there. However, I decided I didn't really have enough time to do everything. So, but if somebody wants to ask a question at the end, I will do my best to answer. I don't have slides prepared on this last topic. Okay, let's go to the very beginning. So magnetic reconnection, you, for example, have oppositely directed magnetic fields. And you can imagine simply those reverse magnetic fields annihilating each other. And of course, that means that there's going to be energy released. And the real question is, how does that happen in a plasma? So if you take this oppositely directed field and by some mechanism break it off and cross connect it, then you'll get this bent field here. A bent magnetic field has magnetic tension to it. And so this is a giant slingshot, and this slingshot then ejects plasma, which is frozen onto that magnetic field at the alphane speed. And then you get a similar bent field line ejecting to the left side. And the important thing is that when you have oppositely directed flows like this, you get a pressure drop in the middle. That pressure drop pulls in plasma from above and below. And then you, by magic, again, reconnect that field line, and the whole thing then is self-driven. And it turns out that the breaking of the field line requires some dissipation process. And this occurs at small spatial scales because dissipation tends to be weak. So the region where you have broken field lines then is a very small spatial domain. And the reason I sort of discuss all this is that if you look in the literature, you keep seeing this mention of stuff pushing from the outside, driving reconnection, but that's not what it's all about. Reconnection is self-driven, and there's no external forcing required. Okay, so here's the classic resistive MHD description of reconnection back from Sweet Parker days. And in this MHD description, you have a highly elongated current sheet of some macro scale with a current sheet that it's controlled by plasma resistivity. And because resistivity tends to be weak, that's a micro scale. So you get a highly elongated current sheet. And because of that high elongation and the requirement that whatever comes in to the current sheet has to go out, the constraint on number conservation or continuity tells you that the inflow speed is this width, this micro width over the macro length times CA, which means you have very slow reconnection, much less than the alphane speed. Whoops. And this slow reconnection is simply not consistent with the observations. So MHD predicts a macroscopic nozzle and a result which is sensitive to resistivity, and that's not consistent with observations. So, and this problem then goes back to the 1950s, trying to understand that. Okay, so there's been many, many observations of reconnection in the Earth space environment. And so here is a nice example from a paper by Tai-Fan in 2006. And I show this to establish that reconnection can be a macro scale phenomenon. This event was observed by 3 separate spacecraft. You can see them here. Here's wind, here's cluster, and then you've got ACE. and their total separation was of order 390 Earth radii. And what you can see here, as a function of time, the reverse magnetic field here, here, and here, and the outflow jets in the blue and the red, and here, and here. So this establishes that reconnection is macroscopic, and that means you can have energy release in a macro system. Okay, so let's see. So I want to talk about the mechanisms for fast energy release. In particular, how does one go beyond MHD, traditional MHD, let me say that, to produce the fast rates of energy release seen in observations. So there's basically, I split this into two basic categories. The first is so-called Hall reconnection, where you get an open outflow exhaust. So here it is, here's a picture from a simulation. Instead of having a Sweet-Parker layer, you have an open outflow exhaust. This is similar to what was predicted by Harry Petchek, although there are some differences, and I'm not going to go into detail about those differences. But anyhow, that you get an open outflow if you do a simulation which includes the Hall terms, was established many, many years ago by a number of different groups. And then the second mechanism is what I call multi-island or multi-X-line reconnection. And again, here's several authors. And the idea is that when you look at the Sweet-Parker current layer, it actually breaks up into many magnetic islands and many X lines. And those many X lines and those islands allow flux to be ejected at a much higher rate than predicted by the original Sweet-Parker picture. And so you can have a current layer with many islands that produces pretty fast reconnection. So this is the second dominant mechanism for fast reconnection. And I have just a couple of movies here showing what's going on. Here's the multi-island regime. You can see the movie, and you can see multiple X lines forming one after the other. And if you look at that, it's just a continuous process of multi-island formation and ejection. And if you plot the flux coming out of the exhaust region at either end, it takes on a bursty behavior as these islands carry particles and magnetic flux out of the current layer. This type of behavior is important for resistive MHD model. In other words, the Sweet-Parker model completely breaks down if you have a very low resistivity. And this type of behavior also exists in the kinetic description if you have a strong out-of-plane magnetic field, the so-called guide field, and you're at low beta. So you can get pretty fast reconnection with this multi-island type system. And the second mechanism is basically the Hall type system. So here's a movie showing that. You get an open outflow. You can see there is a secondary island forming there, but not so often as in the previous example. And so you get this fast reconnection with an open exhaust. And then showing the flux down here versus time, you see that it's basically fairly steady. This is most relevant for the magnetosphere. It's a collisionless system with beta that's not too low. And so this type of behavior dominates in the magnetosphere. Okay, so an important development in an understanding of reconnection had to do with in exploring the structure of the diffusion region where reconnection takes place. Here's the X line, is the decoupling of electron and ion motion in collisionless reconnection. And the idea is that as you have plasma flowing in from below and above, because of the different masses of the electrons and the protons, the protons come in and they sort of turn the corner and start heading out at a scale size, which is the so-called ion skin depth, C over omega pi. But meanwhile, the electrons, because they are, their mass is so low, maintain their magnetization until they get much closer to the X-line, until finally they break free of the magnetic field at a scale size, which is the electron skin depth. And that gives you two distinct scales, one associated with the ions, which is the ion skin depth, and one associated with the electrons, which is the electron skin depth. And those differ by the square root of the mass ratio. Now the ions get ejected out with basically the alphane speed, as we discussed previously, on either side. However, the electrons are not controlled by the alphane wave dynamics because the scale size is too small for alphane waves to exist. And the electrons very close to this, in this narrow region here, are actually controlled by Whistler wave dynamics. And the peak outflow speed that the electrons can gain is the electron alphane speed. Whoops. And that is the square root of the mass ratio larger than the alphane speed. So what happens is the electrons get ejected with high velocity, and then they have to slow down there to join up with the ions. Now, if you look at the current loop that's formed as a consequence of what I just described, you have a very high velocity jet of electrons coming out here, and that gives you a current which wraps around like this, and that forms these so-called quadrupolar out-of-plane magnetic fields, and they're drawn in this picture here. This picture actually came from Marit Orset in 2001. Okay, so one of the predictions of this two-scale situation is this quadrupole magnetic field, so-called Hall magnetic field. And one of the first confirmations of this picture was the measurement of that quadrupole field in the magnetotail. And here's some of the early papers on that. And this shows, here's Bx, which tells you whether you're above or below Bx in the magnetospheric tail coordinate system. Tells you whether you're above or below the midplane, and then Vx tells you whether you're down tail or towards the Earth. And you can see that you see these out of plane fields, which are black in the two quadrants and red in the other two quadrants. So this is the quadrupolar magnetic field due to the decoupling between electrons and ions. And experiments have seen this also, and simulations, of course, produce this. Here's the out-of-plane magnetic field, dark and light, meaning there's opposite signs here. The Hall magnetic field can extend large distances from the X-line. And in the simulations, this can be tens of REs from the X-line, so very large distances. Okay, what about the rate of reconnection? And what I'm first going to do is show you the results of simulations, and then we'll start discussing about the trying to measure this rate of reconnection in the observations. The simulations pretty much universally give you an inflow speed, which is about 1/10 of the alphane speed. And this fast reconnection, this is fast, it's 1/10 of the alphane speed, is independent of the electron-ion mass ratio, which is always artificial in simulations. And most important, it's independent of the domain size. And this has a long history now of work that's basically established this. And of course, that the reconnection rate is independent of domain size in these simulations is important because PIC simulations are highly artificial since they are focusing on extremely small scales. And so they're highly unrealistic from that point of view. And so here's just a result from the Shea 2007 paper showing the rate of reconnection versus time. This is for a mass ratio of 25, and you notice what the rate is. Here's the mass ratio of 25 and 100, showing they're about the same. And then 400 and 25 comparing, it's pretty much the same. And the system size behavior is also, there's no system size behavior. So the simulations reveal fast reconnection. Now, trying to measure the reconnection rate pre-MMS was a real challenge because the inflow speeds, which are a fraction of the Alfvén speed, are very hard to measure because they're below the ion thermal speed. And the other important thing is, and I'll show a picture of this later, is that the Hall electric field that's associated with the Hall magnetic field is very intense. And because that field is very intense compared to the reconnection electric field, it's hard to distinguish the two. And I'll have a little bit more description of that later. So pre-MMS, directly measuring the reconnection rate was extremely difficult. What about breaking field lines in collisionless reconnection? And there was a lot of earlier work on this, and I think Michael Hesse deserves a great deal of credit for trying to sort this out. Turns out that momentum transport associated with thermal motion in the X-line region can break field lines, and that's described by this so-called off-diagonal pressure tensor, and you get a balance of the reconnection electric field by that off-diagonal pressure tensor. And so there's a lot of beautiful work done by Hesse and collaborators that have demonstrated this. Now, historically, people have for years invoked anomalous resistivity, in other words, turbulence in the diffusion region, as a mechanism for breaking field lines. My former student, Haihong Che, has a paper on this, and there's been a lot of other work on this. And the idea is that you have strong electron ion streaming near the X-line, that drives turbulence, and then enhances the effective drag between electrons and ions. So it's pretty clear that this is likely to be most important in low plasma beta systems, where the streaming velocity of electrons can exceed the thermal speed. However, this whole issue as to whether it's important, especially in the case of the magnetosphere, is still an open topic of discussion. And I think there's disagreements in the field about whether anomalous resistivity is important. I'm not going to spend a huge amount of time in this talk, but I will show you a few things. Okay, so I want to now start saying something about MMS observations, and I'm going to focus strictly on the Magnetopause. MMS has made thousands of crossings, and magnetic reconnection has been documented in hundreds of these events, and I'm just mentioning phase 1, and I don't have a count on the number over the whole history now of MMS, but I just looked under phase 1, and so hundreds of events have been seen. The location of the events at the Magnetopause is generally consistent with this so-called maximum shear model of Trotner's. And in particular, what this model says is that reconnection takes place where the rotation angle between the magnetospheric field and the draped magnetosheath field is the greatest. I'm not going to talk about this in great detail because the focus of my presentation is more on the structure of the electron diffusion region at small spatial scale. And clearly, because the electron diffusion region is very small, the number of crossings of this region is much more rare than reconnection in general. In any case, that's going to be the focus of the rest of my talk, is on the small scale structure. Okay, so the magnetopause is somewhat different than what I've discussed up to now because of the asymmetry in the system. In particular, here I've drawn the magnetosheath magnetic field pointing downwards. So this is the region downstream of the Earth's bow shock in the magnetosheath. I've drawn it with a southward magnetic field, and then you've got the magnetospheric magnetic field pointing up. And the important thing is that there's a huge density drop from the sheath, which is high density, to the sphere, which is low density. This can be up exceeding a factor of 10. And that makes a big difference. In particular, there's been a lot of work at this historically, but the Kasich and Shea 2007 paper was an important contribution. And one of the things they did was to try to figure out how does the combination of the density in the sheath and the density in the magnetosphere combine to give you the outflow speed. But I want to bring up something which I think is more important, and that is that the stagnation point of reconnection, which for a symmetric case was centered around the X line, is now shifted. And in particular, the stagnation point of the flow is now on the magnetosphere side, and the current is peaked on the magnetosphere side rather than the X line. And this is going to be an important thing which we're going to talk about from the point of view of the MMS observations. And this is because the ions come in here with high density, and they okay, let's see here. Too sensitive. The ions come barreling across the reconnection region here and out, and they overshoot the X line. And so the stagnation point in the flow is over here. And so what I'm showing here down below is a cut through a PIC simulation of this result through the X line. And I lost my cursor. Well, here we are. And so here's here's a cut across the magnetopause. Here is the magnetic field. This line marks the X line. And the yellow is the flow I've written in terms of the electrons. And you can see the stagnation point of the flow is to the left of the X line, which is on the magnetosphere side. Here's the density, the sheath, and the magnetosphere. And here's the real surprise, and that is that the current is peaked not at the X line proper, but on the magnetosphere side. And why is that? That's because I keep losing my cursor. Okay, here we are. That's because there is a very large normal electric field set up. The ions come barreling across, and they're effectively unmagnetized in this region, and they're held back by a very large normal electric field, which is pointing towards the sheath. And so here is that electric field, E normal. So the ions come barreling across, and a E normal holds them back because they don't want to leave the electrons in the sheath. And you can see that normal electric field, here it is. And so basically it's the E normal electric field that holds back the pressure gradient of the ions. And so the ions are basically nearly unmagnetized. And this E normal is generic to asymmetric reconnection. And what you notice here is that the profile of the E normal overlaps very well with the electron current, the out-of-plane current. And this out-of-plane current is basically driven by that normal electric field. It's an E cross B flow, and it doesn't peak at the X line, it peaks on the magnetosphere side of the X line. So it's not localized near the X line. Okay, so what you're going to see is this is playing a prominent role in the MMS observation. So this is a very important point. The importance of E normal to this whole reconnection problem at the magnetopause. Okay, so I'm going to show you the famous MMS October 16, 2015 event, which was, of course, discussed by Jim Birchett in his paper in 2016 Nature paper. Okay, so here is that event, a simulation with that shows the MMS trajectory through this region, and it crossed back and forth between the magnetosphere and the sheath. The sheath is on the left here, and then crossed very close to the X line through here, where it saw the structure of the electron dissipation region. So I want to point out some important parameters for this. So here are the magnetic fields on the sheath side and the sphere side, and the density in the sheath and the sphere. You notice a very large density ratio, Alfvén speed of about 150 kilometers per second. This was basically anti-parallel reconnection. Okay, so what do you expect to see with these parameters? And what do you expect to see? And I'm basing it on reconnection simulations of this thing. You expect to see a reconnection electric field of 0.2 millivolts per meter. You expect to see out-of-plane currents, the reconnection-driven current, of about 0.6 microamps per meter squared. And the local dissipation rate, J dot E, should be about 0.12 nanowatts per meter cubed. Okay, now this is important because I'm going to contrast with what MMS actually sees. So remember, the electric field, reconnection electric field, should be about 0.2 millivolts per meter, dissipation rate around 0.12 nanowatts per meter cubed. Okay, so here's the MMS observations. This is a relatively long time plot showing the trajectory that I just showed you previously, going across the magnetopause in the magnetosheath. And the reconnection event and the electron dissipation region is in this small region right here. And you can see the reversal in this is in so-called minimum variance coordinates, where L is the reconnected electric field, N is normal, and M is the out-of-plane direction. Okay, so here is the crossing of the dissipation region. It's shown by this little red blotch here. And you're measuring, if we go down here, you can see the currents. Here they are, very intense currents. And the electric fields, which are down below here, highly bursty electric fields. And you notice that they're not at 0.2 millivolts per meter. They're more like 10 millivolts per meter. So more than an order of magnitude greater. And the current, of course, is also highly bursty. So these electric fields are much greater than the reconnection electric field. And an important other observation is the so-called crescent distributions of electrons. So this is in the perpendicular plane to the magnetic field, you see a crescent. So what is that crescent and why is it there? So I'm going to talk about all these things which you did not expect, these large electric fields, much more intense currents, and then the crescent distributions. We'll talk about all of those. So here's a blow up around the diffusion region. Okay, so here's the magnetic field coming in, and you see that the reversal, the null point is right here. And now let's look at where the electric fields are. And you can see that they're not at the X line. There's highly bursty electric fields on the sphere side. And you look at the current. So here's the current. This is the out of plane current, which describes the reconnection driven current. And you notice it's not at the X line at all. So for years, we were looking for these intense currents at the X line, but that's not where they are. They're over here. And you look at the dissipation. It is not at the X line. It is over here. And not only that, it's taking on these values, which are up to 150 to 100 nanowatts per meter cubed. And remember what I told you to expect based on predictions was 0.12. So the theoretical models were off by more than 2 orders of magnitude. And that's a very sobering thing. Okay, so, and not only are these dissipation rates or energy exchange rates extremely large, they take on positive and negative values, and that's really weird. You want this to be positive if you're dumping magnetic energy into the plasma, but instead it takes on positive and negative values. Why is that? We need to figure that out. So the fact that these electric fields are so turbulent also makes you wonder whether there's actually a turbulent dissipation mechanism going on here. Okay, so let's now talk about these crescent distributions as seen in the data, the MMS data. Okay, so remember that normal electric field that I mentioned previously. So here it is. There's a very intense normal electric field across the X-line region. And that has a huge influence on the electron dynamics near the X-line. So imagine you've got electrons here. There's a very intense electric field pointing to the right. Rats. Those electrons execute cusp-like orbits. So here they are. Here's the X-line. And the electric field, this is a very weakly magnetized region. The electrons get ejected towards the magnetosphere, and then they turn around in the magnetic field and they come back, and then they get injected again, and they get this distinct cusp-like orbit. And that was discussed in the Birch paper by Besho and Shea in 2016. These cusp-like orbits are the reason for the crescent distributions. The crescent distributions, these orbits are in the plane, the local plane, perpendicular to B. You can see the magnetic field is pointing in on this side over here. And this is the source of the crescent distributions. Now, actually, these crescent distributions were first seen by Michael Hesse in simulations in 2014. Okay, well, these crescent distributions are really important. And the reason is because this electric field sweeps the electrons out of the X-line region. The electrons get ejected out. That's why you don't produce any huge current here, because the electrons get ejected out by that electric field. So it sweeps the electrons away from the X-line and therefore limits the current at the X-line. And this helps facilitate reconnection. There's very little in the way of intense current at the X-line. And these crescents, as measured by MMS, established that these electrons were being swept away from the X line by that normal electric field. And that's why I consider this to be such an important observation. Okay, let's talk about oscillatory energy conversion. Again, this was something which is unexpectedly seen by MMS, and the intense dissipation was orders of magnitude more intense than we expected from earlier simulations. And Mark Swistak has a 2018 paper in which he has figured out why this happens. And the answer is that instead of getting a nice, smooth dissipation region, you actually see a dissipation region in which the J dot E, the dissipation, looks like this weird plot here, with extremely large positive and negative values, which are the same order of magnitude as seen in the MMS data. And this is not turbulence, it's a standing structure. It just sits there for long periods of time, so it's not like waves moving back and forth. This is a standing wave structure in the electron dissipation region. And this comes about because of beams of electrons flowing along the separatrices that converge and jet across the X line. You can see that here. And it's a bit small, but anyhow, electrons come barreling along the separatrix here and get ejected across the X line, and then they bounce. And they bounce because their orbits are large, the magnetic field is weak here, and these electrons have very high velocity. They bounce back and forth. And remember that this is a very large E normal. Here it is. And those electrons are bouncing back and forth across E normal, and that means they're extracting and then taking energy from that E normal electric field, and that's why you see these positive and negative values. Electrons come down here, they gain energy, and then they bounce back and forth, and they lose energy, and that's why the oscillatory dissipation. And it's a big surprise, but the dominant J dot E is actually JNEN, and this has been confirmed by recent MMS observations. And that actually corresponds to dissipation of the Hall magnetic field, the out-of-plane component of the magnetic field. So this field gets annihilated in this intense region here. Okay, so let's talk about the rate of reconnection and the challenges in terms of measuring that. And so I'm illustrating the problem by showing you a simulation of symmetric reconnection. And what I want to show you is the normal electric field. So here's symmetric reconnection. That also has a very high normal electric field. And here it is here. This is so-called Hall electric field. And the point is that this normal electric field is extremely large, much larger than the out-of-plane reconnection electric field. Okay, and that means it's very difficult to disentangle the reconnection electric field from the other electric fields that are in the dissipation region. And the point is that when you're doing a minimum variance analysis of this structure, if you mess up a little bit, then you're projecting this very large E normal into the M direction, and that means you're messing up the reconnection electric field by a large amount. And this was discussed in a 2018 paper by Genestretti. So that means that measuring the reconnection electric field is the challenge. Okay, on the other hand, if you go very close to the X line, then the inflow and outflow electron velocities become very large. And that's because these velocities scale like the electron Alfvén speed. And the electron Alfvén speed is huge. It's much larger than the Alfvén speed. And that's again because the dynamics there is controlled by the Whistler wave rather than the Alfvén wave. Okay, now MMS has been able to measure these high-speed electron flows and the associated electric fields at the magnetopause and in the magnetosheath. And Jim Birch has a very nice 2020 paper that talks about this. And so here I'm showing you a slide showing you some of that data. And so this is an April 15, 2018 event. And here is the reconnecting magnetic field, the L component. And again, you notice that the null point is here, but all the action is actually over here on the sphere side. Again, this is magnetopause. And what you can see here, here's the out-of-plane current carried by the electrons. And what I want you to focus on is this red, which is the normal electron flow speed. And you notice it has a bipolar signature, plus and minus. This is the inflow velocity into the current layer. And it's, of course, switches sign on either side of this intense current layer. So this is the inflow rate seen by MMS. And they are able to measure this because it's a very high velocity compared to the typical lower velocity flow, subalfvénic flows. And you notice again that this is on the sphere side of the system. Now, if you want to figure out the reconnection rate, you have to normalize to the electron Alfvén speed. And we had a paper in 2008 which discusses all this. And not only that, you can't normalize the electron Alfvén speed upstream. You have to normalize it to the electron Alfvén speed right upstream of the electron dissipation region. And that's what Birch et al. Did. And here's a blow up of that region. So again, here's the magnetic field. This is the magnetic field just upstream of the current layer. Here's again the reversal of the electron flow speed. Here's the out-of-plane current. And you can calculate then, and this is now written in normalized units, E normal over the electron Alfvén speed. And you can see how big it is. It's about a little bit more than a tenth. And in fact, the inflow speed is about 0.14 times the electron Alfvén speed. So this is a direct measurement of the inflow rate and therefore the reconnection rate. And similarly, they measured the electric field. And that course, I'm writing that in velocity units. And it was written that way in the paper. CEM over BL is 0.04. So you can see that there's not perfect agreement, but that agreement, they're still getting inflow rates, which are a fraction of the electron Alfvén speed. So this is very nice preliminary measurements of the reconnection rate, direct measurements of the reconnection rate. And clearly both of these measurements have uncertainties that require further exploration. So I'm almost finishing here. Let me just say one more thing, and that is electron-only reconnection. This is a very important topic. And one of the reasons is because many people have been asking whether magnetic reconnection plays a role in the dissipation of turbulent cascades. These turbulent cascades exist throughout the universe. And the fundamental question is what dissipates the energy when you get to very small scales? And in particular, does magnetic reconnection play a role of dissipating that magnetic energy at very small scales? And this would require electron-only reconnection because the ions orbits are simply too big to participate. So Typhon has a 2018 Nature paper based on observations in the magnetosheath downstream of the burst bow shock. MMS 1 and 3 were on opposite sides of a reconnecting X line and measured oppositely directed outflows. No reconnection-driven flows accompanying this event. No reconnection-driven ion flows accompanied this event. This event had a strong guide field. And so this was an important documentation of electron-only reconnection. I'm running out of time, but anyhow, here it is. Here's the reverse magnetic field for the two spacecraft. Here's the electron outflow going in one direction and in the other direction on the other side. And Birch et al. Went back and looked at this again. The electron out phase speed was almost 1,000 kilometers per second, and the normalized reconnection rate was 0.25 times the electron out phase speed. This is huge. We still don't understand why this should be so large. The simulations are not yielding such large values. Anyhow, direct measurement of the inflow rates. And that's pretty much it. Here's my conclusions, but maybe we're better off going to questions rather than trying to go through these conclusions. Thank you.
Thank you, Professor Drake. Very wonderful, clear lecture. Before we go to questions and comments, I'd like to be asked to be allowed to make a personal statement. It was 45 years ago this month that I walked into my first course at UCLA and found Professor Drake as professor, and he was just as enthusiastic, just as exciting then as he is now, and that started my career of physics. Thank you very much.
Well, thank you, David. It's nice to hear that.
It was an inspiration then and still is today. We have several questions, and I hope more people will come in with questions. Lynn Wilson from NASA Goddard Space Flight Center is curious. I don't know the slide number, but his question is, why is the onset of a finite reconnection rate delayed by a factor of 2 for ion to electron masses of 400 versus ratios of ion to electron masses of 25? That is,
you're talking about Mike Shea's paper.
That is, why does it happen so much earlier in the lower mass ratio simulation?
Okay, let me look. I don't remember ever thinking about.
Or is it just the mass ratio control?
So hold on a second. Let me look at this. This is the this is the one, right?
Yeah.
Okay, what's the issue then is, okay, yeah, so there's a shift. Yeah, he's pointing out, and honestly, Lynn, I really hadn't thought about this. Oh, sort of weird, but yeah, so what you're saying, oh, I see. So yeah, the idea is that the high mass ratio case is delayed compared to low mass ratio.
Yeah.
And what I have to say, I don't know. In fact, I just never sat down to think about this because we were so interested in staring and noticing that the reconnection rate was the same, that it didn't occur to me that there was also a delay. And so I don't know what the answer to this question is.
Good question, Lynn. Thank you. Now, there are a couple of questions about slide 21. The first question is from Boris Petrovich in Brazil, and he's interested about, I believe those are standing waves, you said.
Yeah, they're standing waves. They don't propagate. They just sit there.
He's interested in oscillation frequencies associated with them or associated with the electrons that come in. Do you know that?
They don't oscillate. These are standing structures.
Right.
And the electrons dynamically move through this, of course, and they execute, let's see if I can find my cursor.
He's interested in the bounce frequency of the electrons.
Oh yeah, you can calculate this. I don't remember off the top of my head, but the electrons come through here and they bounce. And that bounce motion is linked to the size of this normal electric field, combined with the the gradient in the magnetic field. So it's a combination of the electrons moving across here, hitting this magnetic field here, turning around and coming back. So it's and in fact, this bounce motion and its frequency was discussed in these papers on the cusp motion and the crescent distributions in these papers, which I show here. So I think I would refer you to the Béchot and Shea papers for a discussion of that, because the bounce frequency is basically the same.
Okay, excellent. All right. Please stay on 21, I think, slide 21. And Tom Hill from Rice University says, the simulations show smoothly varying background fields. The magnetopause doesn't have smoothly varying fields. Is the difference apparent in the comparison of simulations with observations?
Okay, so number one, totally agree with the statement because this is a 2D simulation.
Mm-hmm.
And in a 3D simulation, you see highly turbulent electric fields, just very similar to what I showed from the data slides. Mm-hmm. But nevertheless, even though there's strong turbulence, these structures do still survive in a three-dimensional system, even though it is more complicated, like inferred by this question. So, like I said, I was originally planning on talking about the turbulence that develops in a 3D, a realistic 3D system. And of course, you saw from those MMS slides that those electric fields are highly turbulent, and those are seen in the 3D simulations, but I just felt like I didn't have time to talk about that in this talk.
Okay, we'll have you back. We have a question from Sergei Apatenkov, and it says, clearly the reconnection rate is affected by uncertainty in the LMM coordinates. But on the other hand, E dot J, the dissipated energy, shouldn't depend on the coordinate systems or any errors in them. Can we reliably believe in the observed E dot J values?
Yes, you can believe the E dot J values because that's a scalar quantity and it does not depend on your coordinate system. Of course, that's the nice thing about J dot E. Mm-hmm. But as you can see here, the J dot E that we're actually getting, and in fact was seen in the MMS observations, mm-hmm. Here it is. This has nothing to do with the reconnection electric field times the out-of-plane electric current. This very high value is associated with the JNEN, and therefore this J dot E does not tell you much about the rate of reconnection because it's dominated by things which are not giving you a direct measure of the reconnection rate.
Understand. There's a question from Lisa Antonova in Moscow. What is the role of electron reconnection in the destruction of the magnetopause pressure balance?
Okay, so wait a minute, read that one again.
I'll read it. What is electron reconnection in the destruction of magnetopause pressure balance?
Okay, so you were sort of broke up there, David.
I'll try again.
So electron, we have not, it has not been established that there is electron-only reconnection at the magnetopause. Where it has been established is in these observations in the sheath that came about, that Daifan identified. And so I'm not sure then how to answer this question. In the context of the magnetopause, I'm not aware of anything along this line. I would say, however, that as I was mentioning earlier, clearly the region here, the magnetopause reconnection, is a turbulent process. You can see that the J dot E is messy with highly peaked values, and the electric fields are also extremely messy. And this means that there's strong turbulence going on here. And I'm not sure if the person asking the question is really asking about this strong turbulence or not, but there's clearly strong turbulence, and that's clearly playing a role in the dynamics, especially in the dynamics of the current that's being driven on the magnetosphere side of the null region.
Okay. The last question is actually a speculation. And this speculation is from Richard Denton. And he speculates that perhaps the more massive electrons having more energy are noisier, leading to a faster transition to macroscopic reconnection from a higher noise floor when answering Lynn Wilson's question. So he's referring to Lynn Wilson's question and speculating its electrons with more energy are noisier, leading to a faster transition to macroscopic reconnection.
Okay, so unfortunately, keep in mind that Richard Denton is my former student. In fact, Richard Denton was my first student at Maryland. But I don't think he's right about this, because when we did, and I didn't say this, so he can't be blamed by drawing that conclusion, because in those simulations, we imposed an initial perturbation to trigger reconnection. It was not triggered by noise. So I think that's probably not the case.
I see.
For this result. But it's interesting that I have to say to Lynn that I never even thought about this delay issue and what caused it. So it's an interesting question.
Lynn has a sharp eye.
Yeah.
Okay, so there are no further questions or comments. I'd like to thank Professor Drake once again. This was a wonderful seminar. It will be available online within a few days on the website for this seminar series. I'd like to remind everybody that next week, Jimmy Rader will be the speaker. He will be talking about global magnetohydrodynamic simulations. And I'd like to thank everybody for joining today. We'll see you in a week's time. Bye-bye.